Hello, my name is Frank Palma Gomez. Today I'll present our work titled A Low Resource Approach to the Grammatical Error Correction of Ukrainian. First, I'll introduce our two systems that participate in the shared task. We place first in the GEC only track, and second in the GEC fluency track. We use two approaches that leverage pre-trained language models and synthetic data. Model 1 is an off-the-shelf MT5 model, pre-trained on synthetic GEC data, and further fine-tuned on gold data. Model 2 is a seek-to-seek transformer trained from scratch using GEC synthetic data, and then further fine-tuned on gold data. Our contributions are the following. We propose a two-stage fine-tuning strategy that provides a large performance boost compared to an MT5 model fine-tuned only on gold data. We also propose a novel method for generating synthetic errors using back translation. Unlike previous approach that used back translation, we do not use the full sentence translations as synthetic data. First, I'll discuss our methodology to generating synthetic data. We experiment with two data generation techniques for low resource settings. First is the baseline, which is spell-based transformations. And second is back translation, which is confusions obtained from back translating a monolingual Ukrainian corpus into another language and back. For spell-based transformations, we replace words in a sentence with other words that are commonly confused based on edit distance obtained from a dictionary available in a spell checker. In the example, in the sentence, Carl is an athletic basketball player, the word athletic can be replaced with athletics, athletically, etc. to create a synthetic grammatical error. We use back translation to generate more diverse errors within our synthetic data. Back translation generates more diverse errors that cannot be generated using the baseline spell-based transformations. For illustration purposes, we will give an example in English. First, we grab a source sentence, such as Carl is an athletic soccer player, and translate it to the pivot language. When translating, we generate multiple hypotheses. We then translate each hypothesis back to English, and we align the back translations with the original sentence. In the example, we align athletic with agile, soccer with football, and player with teammate. For each unique word in Ukrainian, the back translated words that are aligned to it are treated as potential synthetic errors. In our experiments, the original sentence is in Ukrainian, and the pivot language we use is English. I'll now introduce the model architectures that we trained. In our first approach, we trained an off-the-shelf MT5 in two stages. In previous works, MT5 was only trained on gold data. First, we train on synthetic data using one of the affirmation synthetic data generation methods, and then we continue training on gold data. We experiment with MT5 base with 580 million parameters and MT5 large with 1.3 billion parameters. In our second approach, we train a transformer seek-to-seek model. This is a smaller model with 275 million parameters. And we follow the same procedure as our first approach, train on synthetic data and further fine-tune on gold data. In our experiments, we utilize the CC100 corpus to generate synthetic data. CC100 contains high-quality data from Common Crawl. To evaluate our models, we report scores measured by Aaron score. Now I'll discuss the performance of our models. In our first approach, we experiment with MT5 base and MT5 large. Our baseline systems, the first two rows, are MT5 models fine-tuned on gold data. MT5 base achieves a score of 53.83, and MT5 large scores a 57.83. We then grab an off-the-shelf MT5 and pre-train it with 2 million synthetic examples. These synthetic examples were generated with spell-based transformations. We find that pre-training on synthetic data boosts the performance significantly by 7 points. MT5 base plus synthetic, the third row, achieves a score of 61.94, while MT5 large plus synthetic, the fourth row, scores a 64.11. Lastly, we find that increasing synthetic data to 10 million examples, the last row, boosts performance by 1 point to a final score of 65.45. In our second approach, we first pre-train from scratch a transformer seek-to-seek model on the baseline spell-based transformations. We use 15 million synthetic examples. Using the baseline spell transformations, the second row, we achieve a score of 60.9. When adding back translation errors on top of the spell-based transformations, the fourth row, we improve performance by 3 points compared to only using spell-based transformations. We achieve a score of 63.3 with this setup. Additionally, when extending the synthetic data to 35 million examples, the last row, we see no significant improvement. Now I'll review the performance of our submitted systems. The first system is an MT5 large model pre-trained on 10 million synthetic examples using spell-based transformations to generate synthetic data. In the GEC fluency track, we combine goal training and validation data and score a 68.09. While on the GEC only track, we achieve a score of 73.14. In our second system, we pre-train a seek-to-seek transformer from scratch using spell-based transformations and back translation to generate synthetic data. On GEC fluency, we achieve a score of 65.96, and on GEC only, we achieve a score of 70.27. We also evaluate our submitted systems by error type. We compute recall per error type for the most frequent error types on the validation set for the GEC fluency track, but we do not compute precision because it cannot be computed since we do not know the system edit types. We find that both systems achieve the highest recall on punctuation and spelling errors, while fluency errors such as flow and style prove to be the most challenging. To summarize, we submitted two systems to the shared task on the grammatical error correction of Ukrainian. We scored first in the GEC only track and a close second on the GEC fluency track. We demonstrated strong results when pre-training on synthetic data and fine-tuning on gold data. And lastly, we introduced a novel synthetic data generation method which extracts confusion pairs from multiple back translation hypotheses. Thank you.